Thank you everyone for joining. It's my pleasure to introduce Josh Fu, who's a Benting postdoctoral fellow at the University of Waterloo, Canada. And today he'll be talking about quantum signatures of proper time in optical ion clocks. The floor is yours, Josh.
Thanks, Navdeep. Everyone can just see the slides.
Yeah.
Okay. Thanks for the introduction, and I would thank Dennis, but I don't think he's here, for inviting me to present our recent work on time dilation in atomic clocks. As mentioned, my name is Josh, and I'm currently a postdoc at the University of Waterloo. And this paper was submitted to the archive a few weeks ago, and you can find it here. For those who don't know me, I was previously a postdoc in Igor Pekovsky's group at Stevens Institute of Technology in New Jersey. And before that, I did my PhD at the University of Queensland with Tim Ralph and Magdalena Zick. So my background is in quantum optics and space-time physics, and I'm broadly interested in applying the tools of AMO physics to probe foundations of quantum theory and gravity in both theoretical and experimental contexts. So just as an overview of my talk, I'll first motivate the subject from a historical perspective, namely measurements of time dilation in optical atomic clocks. Well, not just optical atomic clocks, but also microwave clocks. I'll then describe the theoretical formalism that we use to derive a number of existing effects that have been already measured, including the second order Doppler shift. I'll then show how all measurements of time dilation to date, even with clocks that operate via quantum mechanical principles, can be reproduced via a semi-classical treatment of proper time, in which the quantum dynamics occurs with respect to a fixed parameter. And then I'll show how we can observe effects that cannot be explained via a semi-classical picture of time, instead requiring a kind of quantization of proper time in state-of-the-art optical clock platforms. These include time dilation-induced entanglement for highly pre-squeezed ion clocks and a quantum second-order Doppler shift that arises due to time dilation-induced squeezing of the motion. And then I'll conclude with some summary and outlook. So before I begin, I want to acknowledge my collaborators on this research. So on the left is Gabe Sorchi. He's currently a PhD student at Stevens with Igor. Didi Leibfried and Christian Sanna were our experimental collaborators on this project from NIST and Colorado State. And of course, Igor is the PI of the group at Stevens and also at Stockholm, where the idea for this research started. So as we know, time plays a different role in the different physical theories that underpin modern physics. So in quantum mechanics, time is usually treated as a fixed parameter that governs time evolution in the Schrödinger equation, whereas in relativity, we know that time becomes dynamical and it changes with a clock's motion and gravitational potential energy. Because of what we know about relativity, we should expect that time should behave likewise in our description of the evolution of quantum systems. And indeed, we know that clocks that operate on quantum principles evolve according to their proper time, and so they experience time dilation. So this has been tested in a lot of experiments, with the first direct observation by Hafley and Keating in the 70s, I believe. So this experiment tested time dilation by flying atomic clocks on commercial airplanes around the world and comparing them with identical clocks on the ground. So this confirmed that velocity and gravity cause a measurable difference in the elapsed time measured by a clock. And so since then, of course, the precision of these clocks has improved greatly, and even now the pioneering lab of Junyi has developed clocks that can resolve frequency differences across a millimeter sample of clocks aligned with the gravitational field of Earth. So this is an example of one such experiment where essentially they're able to trap many thousands of strontium atoms in these pancakes, these essentially um, trapping potentials. And this is about 1 millimeter from the top to the bottom, and they can perform differential measurements of the frequency of these clocks of these atoms. And the difference between the frequency of a clock at the top of the lattice from the bottom of the lattice is given by this formula, which is maybe a bit hard to see, but it basically depends on the height difference between them. And so their measurements were consistent with the prediction of the redshift predicted by GR. But as I will explain and hopefully reiterate throughout this talk, this proper time that's measured by these clocks can always be interpreted as a fixed classical parameter probed by a quantum mechanical sensor. So even though they probe aspects of time dilation, even in the non-relativistic Schrodinger equation, they don't probe other aspects of the interplay of quantum theory and relativity, which I will discuss these other aspects as we go. So the first proposal to probe features of time, proper time going beyond this description appeared in 2011 in the work of my former advisor, Magdalena, as well as her collaborators, Fabio, Igor, and Czaslaw. So the idea behind this work is to consider an interference experiment with a clock in a superposition of different heights in a gravitational field. So in the simplest terms, this clock can be modeled as a two-level system with evolving internal degrees of freedom. And due to the universal coupling of mass and energy to gravity, the clock evolves under a superposition of proper times in the different branches of the interferometer. And this leads to entanglement between the internal clock degrees of freedom and the external path degree of freedom. And so the core signature that they showed of this entanglement is a visibility loss once one traces out the clock or the motion. So this expression here shows essentially that the state of the path and the clock will become entangled due to the different clock-dependent couplings along the two paths. So this is the gravitational potential evaluated at some height x. Gamma is the path that is being integrated over. MC squared is the rest energy, and H clock is the Hamiltonian of the clock that governs the internal evolution. And if so, you can see if you prepare a superposition of this path and a superposition of this clock, then over time, this will get entangled, and this will result in a loss of visibility on one of these subsystems via complementarity. Nevertheless, this is quite challenging to perform in practice. So as mentioned, the signature of this time dilation induced entanglement is a loss of coherence. And so this is quantified by the visibility, which in this case is given by this expression. So basically it's the magnitude of the coherence of the reduced state. And so this depends on the energy difference of the internal levels of the clock atom, the height difference, and the time evolution. So the back of the envelope estimate will tell you that basically the space-time area of this interferometer needs to be on the order of 10. So that's like holding a 1 meter superposition for 10 seconds. Beyond the space-time area requirements, to actually initialize a clock in such an experiment and maintain its coherence would be very challenging, even with anticipated advances in atomic interferometry. So we asked a complementary question, given the advances in trapped ion optical clocks, especially the ability to prepare quantum states and have long coherence times and the ability to resolve frequency shifts, we asked the question of whether it's possible to observe quantum signatures of proper time, similar to those predicted in the 2011 paper in near-term experiments in these trapped ion platforms. So as I'll discuss, the signature of time dilation-induced entanglement is observable with a combination of state-of-the-art capabilities as well. And we also derive a quantum frequency shift, which we dub the quantum second-order Doppler shift, that might be observable given significant advances in clock precision. So I'll just give a brief overview of how atomic clocks operate. So they operate via a Ramsey spectroscopy, which is a method for measuring atomic transition frequencies with lasers. So in the top figure, the atom's internal state is basically prepared in a superposition of ground and excited state via some quick pion 2 pulse that rotates the block vector to the equatorial plane. Uh, then the atom is allowed to evolve freely or in the dark for some Ramsey time tau. This is, okay, maybe this is unfortunate that we're using tau here, but it's just some T in the lab. And so if the laser is slightly detuned from the atomic transition, this will precess around the block sphere. And then a second pion 2 pulse then projects this accumulated phase into a population difference between the ground and excited states. And then one measures for example, the excited state population over and over again to gather an interference fringe called the Ramsey fringe. And so the probability of finding the atom in the excited state is maximized when the laser is resonant with the atomic transition. And so what they do is basically lock the laser to this atomic transition and allow it to oscillate with the natural oscillation of the atom. And this is what defines the international frequency standards that you're probably aware of. I also illustrated here what systematic errors and environmental effects can do to this Ramsey fringe. So I've included a delta nu, which is basically a frequency shift that can arise from environmental effects like blackbody radiation or stray electromagnetic fields. And these would stand in contrast to fundamental shifts that we're interested in, which are due to unavoidable phenomena, for example, due to relativity. Yeah, because the clock will undergo relativistic motion in these setups. And then there's also the potential that the clock loses coherence, so it has a reduced fringe contrast or visibility. And this is the reduced amplitude of this dotted line. So what we wanted to do was develop a formalism that can describe the free evolution of the clock during the Ramsey time. So to describe the proper time evolution, which operates at low energies, we conveniently sought out a Hamiltonian formalism, which essentially captures the relationship between the proper time tau and the coordinate time t, with respect to which the Hamiltonian generates time evolution. So for a sufficiently small clock, the total evolution describing both the clock and its motion is given by this Hamiltonian, where h local is just a combination of the rest energy and the clock Hamiltonian. And this arises because the action is given by this expression where L local is the Lagrangian of the local clock degree of freedom, and the Legendre transform is just h local. So the proper time evolution of the clock proceeds as if the rest mass is replaced by the total energy, which includes hc. So for our purposes, we will neglect gravity and consider the clock in a potential V, and we get this expression for the Hamiltonian, and we've neglected terms beyond order 1 on c squared and assumed that the clock energy is much larger than the potential energy. So in other words, the clock frequency is much larger than the trap frequency, where trap frequency is omega and the clock frequency is omega c. This is an angular frequency. And just to clarify, the formalism extends to trap clocks in the presence of gravity. And of course, the original proposal by Magdalena and co-authors was an interferometer aligned with gravity. But here we'll show that even for kinematic time dilation, interesting effects arise. And we're more interested in the core signatures of proper time that cannot be explained semi-classically. So the mechanism behind the effects that I will talk about will hold analogously for the gravitational effects, I think. Well, it's not that I merely think, but it's quite clear to see. So just to isolate these effects, we'll focus on the kinematic time dilation only. So for a harmonic potential, which is a good approximation for the time-dependent electric fields that are used to confine these atoms, we get the following Hamiltonian. N hat is the number operator for the motional modes of the ion's motion, and p squared is the momentum quadrature. Um, yes, in dimensionless units, just for convenience. HC is the Hamiltonian of the clock, and our construction doesn't depend on the internal composition of the clock, but we just take it to be a two-level system for simplicity, in which case H clock takes this form. And so this can be interpreted in two ways. Either it's in this extra term includes mass energy equivalence, which is sometimes called the mass defect in purely classical descriptions, or it can be interpreted as including relativistic proper time to first order in 1 on c squared. And it only deviates from the usual picture by this last term, of course, which couples the clock and the motion. So as mentioned, we modeled the clock as a two-level system with states G and E, and at energy 0 and h bar omega c, respectively. It's useful for us to introduce this dimensionless quantity epsilon c, which basically compares the clock energy to the rest energy. And this clock frequency parameter is related to the trap frequency parameter epsilon m. So m is motion, c is clock throughout this talk. It's related by this relationship. And so just as a figure of merit, for aluminium ion clocks, I think this was Didi's clock of choice for various reasons. At 267 nanometers and 2 pi times 20 megahertz trap frequency, epsilon m is 10 to the minus 18, epsilon c is 10 to the minus 10. And just as a clarification, I use ion and atomic clocks interchangeably throughout this talk, but I think technically they use ion clocks because they're advantageous for trapping in these experiments with electromagnetic fields. So the unitary evolution generated by the Hamiltonian is given by this composition of a phase due to the free evolution, single mode squeezing of the motion dependent on the internal state of the clock, represented by this operator dependence on zeta, and some clock-dependent harmonic evolution that is also dependent on the internal state of the clock. So these parameters are given by this, and this basically can be solved analytically, which is how we arrived at this decomposition. But lambda here is essentially responsible for changing the natural oscillation frequency of the harmonic motion of the clock in the trap. Since it also depends on epsilon c, we'll see how it induces a frequency shift in the clock evolution as well. So we assume that the clock is prepared in a symmetric state with the motion in some general state phi m, which can also be mixed. So the clock evolution is given by this. So this first term leads to an alteration of the usual clock evolution during the Ramsey dark time. And this extra term UCM acting on E phi m generates an additional change in the motional state. And so if we just focus on the first term, we've defined a new clock frequency to be omega prime, and it depends on the number operator of the motion. And this captures the frequency change that depends on the motional state through the motional state of the atom. And as I mentioned, this UCM induces additional effects, but these occur at order epsilon c at the level of the state evolution. So we'll require additional control of the clock and motion to make this contribution observable, but I'll discuss a potential protocol to do this later on. So again, just going back to this state and neglecting UCM for now, we obtain from this the well-known second-order Doppler shift, which has been measured in many experiments. To see this, we can compute the off-diagonal element of this of the reduced state of the clock after tracing out the motion, and this captures the frequency and the coherence. And here the average is taken with respect to the initial motional state, which can be mixed as mentioned. So suppose it is mixed and in some thermal state with some temperature T, we can compute the drop in the visibility, which is basically the magnitude of this, and this loss of visibility occurs at epsilon c squared. So this will be quite small and probably neglected in current experiments. Although, as we show in our appendix, there are some relevant regimes where this can be observable, and it will lead to deviations from the second order Doppler shift, but nevertheless be explained through some sorry, no, well, there will be modifications to the second order Doppler shift, the frequency shift, but in those regimes, if we want to make this observable, then the temperature will be so high that we probably wouldn't reliably be able to differentiate the visibility loss due to time dilation as opposed to simply thermal effects. But I digress. The frequency shift can be read out simply from this off-diagonal element, and it's given by this expression. N bar is just the occupation number of the thermal state. As you can see, we can just basically replace n hat with n bar as we're tracing over the motion. In the high temperature limit, we get kBT divided by mc squared. And this can be related directly to the thermal distribution of velocity divided by 2c squared. And this frequency shift has been measured in many experiments, and it shows the strength of this fairly simple formalism shown here. So this second order Doppler shift simply follows from the time evolution generated by the Hamiltonian after tracing out the motion and reading out the frequency via the off-diagonal element. And it's interesting because the experimentalists usually derive this shift in nearly purely classical terms. So these derivations can be found in the early papers by David Wineland's group, but this thesis by Richard Lang spells out the key ingredients very clearly. Essentially, you can start with some classical equation of motion for the ion's position in the presence of oscillating electric fields used to trap the clock. Omega RF is the frequency of the time-dependent field, and this term gets carried along. But as I mentioned, we just assume that the potential is static approximately. This is just the equilibrium position of the ion. Omega I is the harmonic oscillation frequency of the ion. And this is obviously a very classical looking expression. Qi is just a parameter that depends on the trap geometry, the so-called Matthew parameter. But this can be neglected for our purposes. And so what they do is by the equipartition theorem, they compute the average kinetic energy from the velocity, the time derivative of this, and associate a temperature to each translational degree of freedom. KBT is half mr r squared omega squared. And so the frequency shift, so I'll use these ingredients in this next slide, but the frequency shift of the clock is obtained via the Doppler effect. So basically there's a relative frequency difference between the laser frequency in the rest frame of the ion compared with that of the lab. So the rest frame frequency is nu prime and the lab frame frequency is nu. And so if we expand the gamma to leading order in 1 on c squared and averaging over the duration of the experiment, it gives this expression here. V parallel is the velocity of the ion parallel to the probe laser beam, and this is 0 on the timescale relevant for experiments. And the mean of V is the average velocity over the translational degrees of freedom of the ion, which is r dot from the previous slide. And then plugging in the average kinetic energy as obtained from the previous slide, we simply get this kBT on mc squared formula. And this extra term is from the time-dependent fields, which for our purposes, we can neglect. So unsurprisingly, or maybe it's surprising, there's seemingly very little quantum mechanics in the derivation of this frequency shift. So as mentioned, the second order Doppler shift assumes that the clock is in some highly classical thermal state. So what if we assume that it's in a quantum state, like the motional ground state? Again, we can neglect UCM in the evolution. So even though the clock is in the ground state, it picks up a frequency shift. And this effect arises even though the ion is cooled to the absolute ground state. So this frequency shift can be seen in this perturbation to the usual phase offset between the G and E states. And this arises because of vacuum fluctuations, or more specifically because proper time is velocity dependent and the ground state is not a momentum eigenstate. So it's got some finite spatial extent, implying a finite momentum spread around zero. And so the vacuum second order Doppler shift is thus, it's an example of an effect where proper time evolution is not due to a classical well-defined state, and it doesn't stem from a mixture either. So it's because the clock picks up a vacuum contribution through this expression, through this term in the phase evolution. And so it can be viewed as an observable manifestation of the vacuum. And this is consistent with previous calculations by Magdalena and Rebecca from a few years ago, and another more recent paper by the group of Clemens Hammerer. Nevertheless, even though we have a quantum state and a seemingly quantum phenomenon manifesting in this frequency shift, even this vacuum second order Doppler shift can be interpreted within a model where the clock just undergoes time evolution with respect to a fixed parameter, rather than an operator that possesses quantum properties. In particular, signatures on the frequency, when we average over the motion, they can't distinguish this quantum mechanical description of a Hamiltonian generating time evolution of a quantum system from a semi-classical model in which we replace tau hat with the mean of tau. So what do I mean by this? Let's, for example, expand our coherence to leading order in 1 on c squared, in which case the phase evolution of the clock after tracing out the motion becomes this, where basically the modified frequency depends on the mean of the phonon number operator, which can then be reinterpreted as this shift in the frequency that occurs with respect to the mean of v squared. And what this does is that the clock then evolves according to this mean of tau, and it can be really just interpreted as a shift in the frequency, irregardless of the initial state that is used. So this average is taken with respect to a quantum. It can be taken with respect to a quantum initial state, but nevertheless, it can reproduce any frequency shift via this semi-classical interpretation where clock evolution is just occurring with respect to a fixed parameter. Even beyond this perturbative expansion, the frequency shift can always be interpreted and captured by this average over all motional states. And this admits a classical interpretation. In particular, if we are given some initial classical energy E, and then we average over the initial energies of the motion, then the clock frequency will shift to this. And this is related to a problem that we found in Goldstein's classical mechanics textbook, where he basically computes the leading order relativistic correction to a classic harmonic oscillator. In other words, there are various classical or semi-classical models for proper time that can be used to explain all measured effects, including the ones that we've derived so far. For example, on the left, we have a relativistic clock that undergoes motion in a harmonic potential, and the evolution can be described by this, e to the minus IHC tau. And this is similar to the model tested by Hafele and Keating, where they essentially just compared the pure phase evolution of clocks traveling around the world versus clocks on the ground. In the middle, the clock evolves with respect to a single proper time that arises in average over the quantum motional state. And this is the semi-classical model that can explain second-order Doppler shift and even the vacuum second-order Doppler shift. And then finally on the right, we have this unapproximated form of the coherence. And this gives rise to an interpretation where the proper time is averaged over the clock's classical mixture of motions. And this was what I mentioned a few slides ago, where this fully fledged form of the coherence can lead to new shifts that can become observable in certain regimes. And these are discussed in our appendix. On the other hand, if we measured entanglement, then the outcome of this measurement would be inconsistent with a classical picture of proper time. To explain entanglement, it's really necessary to quantize the proper time tau via the dependence on x and p. But as mentioned, the original proposal is very difficult to implement, which is and it's far beyond the current state of art. But I'll show in the next slides that we can make this observable with some state-of-the-art capabilities. So in particular, this time dilation-induced entanglement can occur even if we neglect this UCM, which I was hinting at is sort of a signature of quantumness due to time dilation. But even if we neglect this UCM, we can see that entanglement can arise through the motion-dependent frequency shift shown in the form of the state here. So here, this frequency shift depends on the phonon number operator. So suggestively, if we use some state that is a superposition of Fock states, this will lead to entanglement between the clock and the motion. So we focus again on the loss of coherence, and we look at the loss of coherence on the clock rather than the motion, which is what Magdalena's original paper looked at, but this is obviously just complementary. And we focus on the clock because that's what the experimentalists are interested in. And so we use a squeeze state, which is, of course, this superposition of Fock states. And this is just a squeeze vacuum. And so the off-diagonal element of the clock is given by this expression. If we set r equals 0, which is the squeezing parameter, we, of course, just recover the usual vacuum second-order Doppler shift given by this epsilon m divided by 4. It also induces an additional frequency shift, but we're interested in the visibility, which is the core signature of entanglement. And this is still quadratic in epsilon m or epsilon c, depending on how you want to rewrite this expression. But with state-of-the-art capabilities, namely for an aluminium clock, which gives epsilon m on the order of 10 to the minus 18, a 20 megahertz trap with motional coherence and clock coherence of 1 second, and a squeeze state of that is generated by r equals 2.26, which is an experiment that was recently performed by Didi's group. This results in a loss of visibility to 0.93. And so this would be observable in state-of-the-art clock experiments. And to maximize confidence that we are observing a time dilation-induced visibility drop, we, of course, would perform some sort of differential measurement using different squeezing parameters and species of ion and so on, just to make sure that this visibility loss scales with this expression. So these numbers, as I mentioned, have been demonstrated in these experiments, including those of Didi's group. And the resulting frequency shift is observable, but the visibility loss is of greater interest since it is the hallmark of underlying quantum dynamics and entanglement between the clock and the motion. And so this goes beyond this classical treatment of proper time dynamics. And in principle, we could do joint measurements of the clock and the motion to directly infer the entanglement without relying on visibility. So just to illustrate this schematically, the top row shows the evolution of the motional degrees of freedom, and the bottom row shows the evolution of the clock. So basically, we prepare a squeeze state of the motion and the clock in the bottom row with some preparation and control over the different subsystems. We then let the two systems evolve via the Ramsey time. the motion undergoes some superposition of different time evolutions. So we get a superposition of squeeze states essentially, and the clock undergoes this n-dependent frequency shift, and these two subsystems become entangled over the course of this Ramsey time. Yes. Okay. So I'm nearing the end, but I just want to touch on this last effect that we derived, which incorporates the quantum contribution to the dynamics captured by UCM. So this extra contribution arises due to the time dilation-induced squeezing of the motion due to the clock motion coupling in the Hamiltonian. This is different to the squeezing discussed in the previous slides, which is initial state preparation squeezing. Instead, this squeezing arises dynamically and can be thought of as a kind of relativistically induced length change of the clock's motion. So the UCM term is given by this to leading order in epsilon, and it's basically the commutator of the squeezing exponent with the modified free evolution of the motion. So for an initially ground state cooled clock, we get this contribution, which is the usual modification to the clock evolution that gives rise to the vacuum second order Doppler shift. But we also get this anomalous excitation to the n equals 2 Fock state. So this is perhaps a little bit counterintuitive or maybe surprising, but basically you'll see if you prepare your ground state clock, ground state cool it, the experimentalist will suddenly see anomalous excitations to n equals 2. And the reason why it goes to n equals 2 is because of the p squared term in the Hamiltonian, which couples even number Fock states of the motion. So in principle, these n equals 2 excitations would be resolved as motional sideband spectroscopy. So now if we want to trace out the motion, the resulting visibility drop is again is quadratic in epsilon c, so that's too small to observe in experiments. But instead of just measuring the clock, we can design a protocol to reveal a linear contribution or a linear signature of this anomalous excitation due to time dilation by measuring both the clock and the motion. So rather than tracing out the motion, we project onto a superposition of 0 plus 2 of the motion, which can be done by basically driving the clock with classical fields resonant with the motional sidebands. And then we need to apply additional clock-dependent operations, basically to change this time-dependent prefactor to a static phase offset. And then we complete our Ramsey spectroscopy and we read out the frequency shift. And this gives rise to what we dub the quantum second-order Doppler shift in our paper. And this is, again, a frequency shift, but it cannot be reproduced by some semi-classical model. Because it only arises due to this anomalous excitation. And it wouldn't arise if we had some semi-classical model. For example, if the clock motion coupling was HC tensored with, or HC multiplying the mean of p squared. So this schematic basically illustrates this anomalous excitation. And so even though the resulting phase offset is now linear in epsilon, even for the aluminium clock, the phase offset is 10 to the minus 10, which is about 4 or 5 orders of magnitude away from their current precision. So it's an aspirational goal, but currently too small to observe. So in summary, we showed how experiments with harmonically confined clock atoms can probe quantum features of relativistic proper time dynamics, which have so far not been observed. We used a Hamiltonian formalism of composite systems as a description of this time evolution that incorporates these relativistic effects. We showed that we can reproduce known results in the literature from this formalism. We showed also that time dilation-induced entanglement and this new quantum second-order Doppler shift can be, observed in principle, the latter a bit further away from experiments than the former. And Didi pointed out that further improvements are impossible. I think they're planning a boron clock, which is even lighter. And this would, in principle, if we kept everything else the same, would lead to a reduction in the visibility to 0.76. So thank you for your attention. That's all I have to say. The archive number can be found here. And I welcome any questions or comments via email or now if you have them. Thanks.
Thanks, Jos. If you have a question, please unmute yourself and go ahead.
Maybe I can start. Hi, Josh.
Hi.
Can you hear me?
Yep.
Okay, perfect. Yeah, thanks. Very nice talk and of course, very interesting paper. I want to ask to understand a little better the motivation to specifically compare, to specifically use a squeeze state to see in the part where you still looked at the visibility, because the intuition is clearly that if one has distribution over Fock states, they will give essentially each Fock state effectively gives different time dilation, and one entangles. And one could also use a mixed state, like some high temperature state, which would also seem to be simpler to prepare. So maybe if you can comment, is there any caveat, or was it just an example, or yeah?
Yeah, thanks. I think to simply answer your question, I don't think there was a direct reason for favoring a squeeze state over a mixed state per se. I think, as you mentioned, the origin of the effect would be the mechanism behind the entanglement would be the same. But of course, with mixed states, you already have some, some classicality in the motion, and so perhaps it is less easy to distinguish from other sources of decoherence that arise in these setups.
All right, but
Yeah,
if you
and
look
that
at
was
the
yeah.
if you look at the internal states, if they are initially products from the center of mass, then perhaps it would be yeah, I'm just putting it out there. I think it could be advantages. This is also a state that we looked at with Rebecca, so I was just even comparing the number, and I think we got for something like a millihertz rate of the visibility modulations that one could get. So that, yeah, perhaps can be compared to what one can get with the squeezing. Okay.
Yeah, I mean, in principle, we did also compute the visibility with the thermal state. Maybe we computed it with something like this to leading order, and it does scale with epsilon c squared and n bar, the occupation number. I guess you would have to prepare a highly thermal state to counteract to the smallness of epsilon c. I'm not sure if that's the same intuition that you got from the calculation that you performed.
Yeah, exactly. So this mean n can be the squeezed or thermal. Okay. Yeah, I think maybe I.
Maybe I just add to this, if I may. So exactly like on this slide, that's exactly the calculation we did initially too, just for a mixed thermal state. And indeed, this could also work. But conceptually, it's still a bit different because this one arises just from classical averaging. Like all the time you have just different motion classically. Whereas for like a pure squeeze state, then it really would be due to entanglement. So in this case, there would be no entanglement generated, but you still get visibility drop just from classical mixing. There's a conceptual difference between those two.
I think it's similar as the starting with in general a mixed state in the interferometer versus a pure state. So entanglement can still be generated, just cannot be read out. So I understand the conceptual aspect. I was just thinking even in terms of observing the effect brute force in the experiment. Is there some difference that would make it now? Let's say asking people, okay, just heat up this poor
Yes,
clock
yes.
versus squeeze it, and then one can worry if the outcome is there, then one can worry what it means. But just even out of curiosity, that could be done. But I think
No, you're
I'm happy
exactly
with the.
right. Yeah, no, you're exactly right. And we also briefly have something like that in the appendix. Actually, I asked the same question to Christian. Hey, can we just at first just heat it up? I didn't see that, but the experimentalists were not happy with this mindset.
Yeah, I guess that was expected. Okay, perfect.
Thanks, Magdalena.
More questions? Yeah, Albert, please go ahead.
Yes. So interesting talk. So my question is a bit more on the interpretation of the results that you presented. So even starting with the simple case of the calculation for basically the motion of the state of the wave packet that you are considering. So it would seem to me that you would get for the second Doppler effect, or the contributions that enter proportionally to this V square, and the mass difference delta M, or the energy difference delta E, or omega C, that there are what I would interpret as physically two slightly different contributions. So the dependence on this delta M, one is, yes, what would naturally be interpreted, or I would naturally interpret as this relativistic time dilation, spatial relativistic time dilation effect. But the other is that, and this is where some of the details that maybe I also would like to discuss, is you use a trapping potential, which is not, in this case would be the same for the two states, but the motion, since you have slightly different masses for the two different internal states, for the atoms in the two different internal states, the motions that they will follow, even quantum mechanically, if you have some wave packet, the central position of the wave packet would follow certain motion, and it will follow slightly different trajectories. This will be a very different, a very small effect of order delta M over M. But then the point is that the classical action, that the phase that you would accumulate anyway, just for a quantum mechanical wave packet, which is proportional, if you wish, to the mass, the total mass, mc squared, times the proper time. Because you have a slightly different trajectory, you will, and that's proportional to m, not delta m. So you will also accumulate a phase that is corrected due to delta m. So in the end, you have two contributions. One, which is if you had really the wave packets for the atoms in the two internal states following exactly the same trajectory, there would be a contribution that would be naturally interpreted in terms of spatial relativistic time dilation. But you have an additional contribution, which typically in this case could be of the same order, which would correspond to the fact that you have, the excited state is following a slightly different trajectory compared to the ground state. And then, the larger phase that it's accumulating, because it's following a slightly different trajectory, would, differ by an amount which again is of the same order of delta m. And so have you thought a bit about that, or can you,
when you say an additional effect that is of the same order, do you mean something that I did not present here, or do you mean
well, from your talk, it was a bit difficult for me to see. I would assume that those calculations were done in a way that the effect I'm talking about is really included also in the calculations. And then it seems a bit more a matter of an interpretation. However, it's a bit difficult for me to follow all these equations and to see exactly, to be sure.
Yeah, I mean, to attempt to answer your question, I think it would the point of highlighting these different classical and semi-classical interpretations of this second order Doppler shift is to highlight that the measurement cannot distinguish, the measurement of the frequency shift, which gives you a single value for the second order Doppler shift, it would not be able to distinguish between various interpretation of what is happening in the dynamics, whether it's this purely classical picture where you have a clock that's just swinging classically in the trap, which is what the experimentalists use to compute the second order Doppler shift with some averaging over this motion, with a Hamiltonian dynamics, which is ostensibly quantum, but yet we still end up with an expression that averages over the motion anyway, rather than just distinguishing two coherent paths that the clock traces out in its evolution. I think that maybe that's the point of the last protocol I described, which is to actually coherently interfere these two paths, which is what we did when we proposed to project onto the motion, and this would yield a unambiguously quantum signature of on the frequency. But if we are simply to trace out the motion, which is essentially an average, I think the upshot of what I'm trying to do when I compare these classical and semi-classical interpretations is that the outcome is still the same, and I don't think you would be able to distinguish the interpretation.
So I think that there's a bit of a confusion on that's not exactly so. I was not even in the classical case. You would have these two different contributions to the total result for the phase that you came.
Sorry. If I may add, I understand, Albert, what you're saying, but I think it's not correct. There's only one contribution, and you can interpret it either as proper time change or as a mass defect, but it's only one. There's no two contributions.
So maybe you are
There's only one.
So you are maybe slightly misunderstanding because so suppose, but maybe we should leave this, however, for the discussion part, because I don't, if some other people have questions, I don't want to take much of the time. But just summarizing, you know, the trying to clarify this point, Igor. So if you express this in terms of, I mean, you have both things. You have the fact that the two different internal states have, you know, slightly different proper masses, and then you have some proper time that there might be some time dilation effects. But in addition to that, those two that you need to take into account together, there's an additional point, which is the fact that in certain cases, like here, you will have slightly different trajectories for the ground state and the excited state, because you have the same, let's say, the same potential, for example, but since you have slightly different masses, they will all follow slightly different trajectories. And so that
and
gives
you're correct, but that is only one effect. That's precisely the effect we are describing. This is one way to understand this effect, that precisely because you have different masses, you have slightly different trajectories, and that is exactly what is happening here. So that is the one and only effect that's happening.
No, there is an addition, but we should leave this then for the discussion. There's another effect, which is that even if you were following the same trajectory, so there's a contribution where you have some special relativistic time dilation. So you have those different contributions. You have to combine all of them. But let's leave this maybe for
but that's precisely what this formalism does. So it has everything in it.
Well,
there could be, for example, let's say there could be, for example, only one mass, and it follows some trajectory. This would be additional contribution p to the 4, which we don't even have. We don't even consider it. So on Josh's first slide, I think he showed that, look, the main energy scale that's important is really from the clock. And so, yeah, there could be like p to the 4 or some other motional contributions of just even a single mass. But those are much smaller. And the only thing that comes about is that the clock itself has essentially two different masses and evolves relativistically. And that is one and the same effect. So in other words, there's two words for it: mass defect or proper time evolution. It's the same thing for a clock.
Well, that I don't really agree with that statement. I agree that your formalism can include all of that in it. So it's more a matter of how you interpret the different contributions and so on. That I don't dispute.
But there's not two contributions. There's only one. And this is the confusion that I've seen actually many times in recent works. And there's the mass defect is simply another word for mass energy equivalence applied to this proper time evolution.
So we agree that mass defect, or whatever name you want to do it, to give to it, is equivalent to this energy difference and mass energy equivalence. That I think we agree on. But that's one aspect. Another aspect is the fact that you have different proper times due to time dilation effects, and then the combination of the two,
no, it's the same. It's the proper time can always be, you can, there's only one, for a mass defect picture, there's only one time. It's either or. So it's one and the same action. So all of these Hamiltonians derive just from one and the same action, which is that it has a clock with two different mass states evolving in proper proper time. So the resulting effect is one and the same, and it's this one, but it's all just contained in the same formalism.
But if your clocks are following different trajectories, I mean, the fact that you have different proper times for the clocks following those different trajectories, that will play a role, and that will combine with the fact that you have, so in the end, the phases that you will accumulate in different cases are proportional to these two things.
But I think I can try to cut the chase, because I think there are the point that Albert is making is that the ground and excited state can follow slightly different trajectories, in which case the experiment is not exactly like a clock in superposition of one or the other trajectory, because kind of part of one clock follows one trajectory and a part of the clock the other trajectory.
That
But
would have been
that's exactly what's here. But that's exactly what this slide shows.
Yeah,
this is precisely
I agree.
What is happening.
So that would have been a follow-up, Magdalena. That would have been a follow-up question or point for discussion. However, we seem to have
my point is this slide shows exactly that. So this slide, what Josh shows exactly that. Yes, those two masses follow different trajectories. This is why there is this new effects arising, such as even the second order Doppler shift can be interpreted in this way. So all of it is comes from the fact that your dynamics is a little bit different of these two. Or Josh, maybe if you go back to the previous slide, the Hamiltonian, it's. But this statement, this additional term of the Hamiltonian, is precisely the one that says, oh look, they have different kinetic energies depending on if it's an excited or ground state. This additional contribution, HC times. So in other words, you're correct. It's just not two different effects. It's only one, all combined in this Hamiltonian. This Hamiltonian contains all of these things.
So that the Hamiltonian contains all those effects, that I'm not disputing. The question is then how you interpret those.
Right. So I think there's always this duality, but there's still an observable signature. And you're right. One can interpret it saying like, look, okay, because the mass is actually slightly different in one case and the other, the trajectory is slightly changed. And that's another way, I think, to interpret the same effect.
Well, I think it's interpreting some contribution to that effect. So the result that you would get in general, that you can get from this Hamiltonian, there will be a total result, and there's some way to interpret the different contributions there that depend on this difference in energies or difference in mass between the two internal states. Then it's more a bit of a matter of an interpretation as in the direction of what Magdalena was pointing out, that yes, this is a point that maybe I would have raised, which is, are you kind of breaking your clock? And then what's happening is that you have, different states following different trajectories, and then you are including their effects that go a bit beyond what would be simply spatial relativistic or time dilation effects. And you include also this effect that because the different parts of your clock, the different internal states in this case, follow different trajectories, you pick a contribution. I believe it's not the only contribution, but in general, you can pick a contribution that also can be of the same order and that corresponds to that. I mean, this we discussed, for example, in some detail in the context of clock interferometry, if you use guiding potentials, because then that's precisely the point. Which kind of trapping potential should you use so that you don't mix up these effects? And there's a little discussion there on the various possibilities, how you can do, and the fact that you are, which is then related also to the second part of another way of interpreting what you were presenting, that you have then, you're in a situation where your potential, is evolving differently, the center of mass states for the two internal states. And then you see this point that you see this loss of visibility that you were just pointing out. But in some sense, someone could say, if you really want to have not to break your clock, what you should be using is ideally some potential where the evolution of the state, the center of mass state of the two internal states is the same, and then you would not see this effect. So you can think in terms of the vacuum state or squeeze vacuum state, as you were discussing here. You could think also of just, some actual motion of the mean position, that it was really sort of sloshing. And then the ideal configuration would be one where you actually have that the motion of the wave packets in the trapping potential of the ground state and the excited state is the same. And then all the contribution that you get can be interpreted just in terms of time dilation effects purely.
But I think in this case it really is, there's really only one effect, which is the motional evolution, and the time dilation doesn't do anything in addition to that. But okay, I think we should discuss separately. But here, at least from this Hamiltonian, I mean, you're suggesting to change the potential a little bit like those states that Magdalena suggested, I think, with her colleague, that there are certain states that are eigenstates of this kind of, basically motion with respect to this mass operator, some kind of generalized coherent states.
I think, in fact, here this would be those. Sorry, I'm lack for words. So there are these not for trapped ions, but for this optical induced dipole, you have this magic wavelength, where for different internal states you can engineer the same frequency of the trap.
Right. So that's what so for example, in the context of
the effect would still be there. Like, in fact, we also we had a quick look with Rebecca, these sort of scenarios where the omega of the trap is the same for the internal states, and there is a very, very small difference in the end in what one gets. So
this is
I don't
looking
know
at
how big advantage there is, because I think also conceptually there is one coupling that is dictated by relativity. And so then enforcing different interpretations, for me, it's like testing against various semi-classical limits. Let's say putting semi-classical motion or semi-classical frequency, and then one can see which model is maybe closer to experiment. But there is not really any wiggle room just starting from quantized interaction. So just, I think, echoing what Igor was saying, that there is just one. There is just one way this can be written, if one, unless one pampers specifically to enforce some kind of semi-classical model, which one doesn't have to necessarily do.
So here there were several things. One is not changing anything, just considering this, and then it's a matter of the interpretation of the contributions, the physical interpretation of the different contributions to the final result, if there are several, how natural it is to interpret those. The discussion got mixed up a little bit in various ingredients that came up. Another one is if you consider using, different potentials. In fact, it's a slight generalization. It would be with optical potentials of the usual magic wavelengths, because the magic wavelengths that are used with optical potentials, in principle, the idea is that you generate exactly the same potential for both internal states. And what you would need really to perfectly isolate only, strictly speaking, time dilation contributions would be to have potentials that lead to the same motion. So that would not be exactly equal potentials. They would differ by a very, very, very small amount, which is of order delta m. And in fact, one can estimate anyway the effects that come from there. I was actually doing that there. And it's just that in your case, you get, that was still like 2-3 orders of magnitude away from what is typically observable. The reason why you see this to be much closer in your case is that for the ion traps, you have these frequencies that are substantially higher than the typical frequencies that they have in the optical lattices. And I think that that's basically why in this context, you might be with the usual parameters kind of closer to this effective and non-negligible contribution. But maybe should let others also that have additional questions.
Yeah, I shall look for if there are other questions. If not, let us thank the speaker for such a nice talk.